Hello everybody. In this video we're going to be giving a proof of the fundamental theorem of calculus, or at least a restricted version of it. There are much more general versions that are out there, but for the purposes of this class, this is what we'll need. Of course, the first observation is that the fundamental theorem of calculus comes in two parts. They're often referred to as the first fundamental theorem of calculus and the second fundamental theorem of calculus. Usually, when you take your first course in calculus, you spend a lot more time dealing with the second fundamental theorem of calculus. So that's this bit you're going to see down here. You integrate a derivative, and then, oh, look at that, it's a definite integral, and I can get the value by simply finding an antiderivative f and evaluating it at the endpoints of my bounds of integration. But the first fundamental theorem of calculus is really useful and important, and so we're actually going to spend some time on it in this class and in this video. In fact, we'll use the first fundamental theorem of calculus to prove the second fundamental theorem of calculus. So, well, why don't we get to it? So, the first fundamental theorem of calculus, in words, is saying, okay, we start with some continuous function f. The rate of change, okay, so when you hear rate of change, right, you should be thinking derivative of the accumulation function. Okay, so that's how we talk about integrals, right? They're accumulating the values of the function f, starting at any point. So the rate of change of the accumulation function equals f itself. So if we go down to this picture, we start with a function f, and we can accumulate. All right, so we accumulate starting at some point c, and we stop at, well, some value x. Okay, and we accumulate all the values of f. Now, once we get that new function, right, which completely depends on x now, we can then take the derivative of that, right? So this is a continuous function, and we want to be able to take the derivative of this continuous function. In fact, it's a differentiable function, at least that's the claim. And if we differentiate it, well, we get some other function, right? And what is that function? And what the first fundamental theorem of calculus says is that this function that we get when we accumulate and then differentiate is precisely the function we started with. Now, if you were originally treating f as a function of t, and then you do this process, you're going to get something that looks like it's now a function of x, all right? But that's just a change in the variable name ultimately, right? What the function does to any particular input, that's not changing. All right, so let's try to prove this. So we're going to, at the end of the day, be taking the derivative of something. So we better write down the derivative. So let's see over here. So this is going to be our proof of f talk 1. And we're going to want to compute the derivative, and we'll say we'll do this with respect to x, of the integral from c to x, right? This is our accumulation function of f dt. All right, so we're going to write down a derivative. Okay, this goes back to your Calc 1 experience. We're going to take a limit, let's say some h goes to 0, of, okay, so I take this function, right? And this is a function of x, okay? And let me, just for now, let me just call this a of x, just to make this easier, right? A for accumulation. So this would be a of x plus h minus a of x over h. Okay, that's our definition, right, of a derivative. Now, it might be a little tricky to see what's going on with this a of x plus h minus a of x because we don't have a good sense of it because we just defined this notation. So let's turn this back into integrals so it's easier to see what's going on. So I have a limit as h goes to 0 of, all right, I'm going to evaluate a at x plus h. So the x occurs here in the upper bound of the integral. So this will be the integral from c to x plus h of f dt. Okay, minus, now we do a of x. And a of x is precisely this integral again. So I integrate from c to x, f dt, and then all of this is divided by h. All right, so what we see here is that we are integrating f from c all the way to x plus h, and then we're subtracting what happens when we integrate f from c to x. So just as a little extra helpful picture here, let's say we put c over here, and this could be x, and maybe this is x plus h. All right? So if we integrate f all the way from c to x plus h, and then we subtract what happens when we integrate f from c to x, then what we'll be left over with is this region when we integrate between x and x plus h. So this will be the limit as h goes to 0 of the integral from x to x plus h of f dt over h. Okay. All right, now it's not really clear how to simplify this anymore, so we have to bring in our first big gun. And that first big gun is going to be the extreme value theorem. So the extreme value theorem tells us that on the interval, say x to x plus h, and we know, of course, f is continuous on that interval because it's continuous everywhere, that f is going to attain some minimum value and some maximum value. So here would be an example. We'll use a little picture here. Okay, so here's an example where we have a function f which is increasing, and on the interval x to x plus h, you see it hits a minimum value actually at x and a maximum value at x plus h because it's increasing. But even if it was decreasing or just going up and down a lot, we know there would be some minimum value and some maximum value. So what we also then know is if we find that minimum value, no matter where it is, then all of the other values of f on that interval x to x plus h are going to be larger than this minimum value, right? Which we could maybe call m of h. Okay, why do I write m of h? Well, because it depends on whichever h we're choosing, right? If I tighten up this interval, if I make it smaller or larger, that might change where the minimum and the maximum occur. Okay, so I know that all the other values of the function are going to be small, or rather greater than this minimum value, and all the other values of the function will be smaller than this maximum value, or at least no bigger than. So what that means is that when I try to figure out what the value of this integral is, right? Remember, this is just accumulation. I know that the value, if I integrate from x to x plus h of f dt, it's going to be at least as big as the area of this rectangle. Okay, that is, I take the smallest possible value of f on this interval and multiply that value, that height here, by the length of the interval. Okay, so the height is m of h. And the width of the interval, right, so this is the interval from x to x plus h, that has width h. So I know that whatever this accumulation function value is, I know that it has to be at least as big as this rectangle. On the other hand, it can't be any bigger than this larger rectangle, right? Area 1 plus area 2, because where do I get this larger rectangle? Well, I take the largest possible value for f, and then I can multiply it again by the width, right? Giving me a rectangle which will be slightly bigger than the area under this curve. So I know this is going to be less than or equal to h, right, which is the width, times capital M of h, right? Or capital M of h, right? That was the largest value of f on the interval. Okay, so here we're using the extreme value theorem, right, to guarantee the existence of those two max values, right? The max height and the min height. Okay, so extreme value theorem. Okay, so that means when I go to compute this limit, I know that the value of this numerator is going to be greater than or equal to h m of h, less than or equal to h big M of h. And so if I divide by h, well, then what's going to happen? I can go through and divide through by all these h's. Now, if h is negative, of course, it's going to reverse, right, the direction of all these inequalities. This is just a subtle detail that we'll have to talk about at the end. Well, let's just assume for a moment that h is positive. So when I divide, all these h's on the outside are going to go away. Okay, so I know then that little m of h is going to be less than or equal to the integral t goes from x to x plus h, f dt, all divided by h, and that will be less than or equal to m of h. Okay? Now, what happens as we let h go to 0? Well, as h goes to 0, we know that this x plus h starts moving in closer to x. And as it moves in closer to x, the extreme value theorem at every step is going to tell you there's a new minimum and a new maximum value. But because f is continuous, those minimum and maximum values, those are going to have to start getting closer and closer to each other. For example, let's say I made my h really tiny, so I started over here. So now you can see that the new m of, right, this new h, so maybe this was h prime, this would be your m of h prime. It's now much, much closer to little m of h. And in fact, in the limit, they're going to equal each other. So m of h and big M of h are both going to be converging to what value? Well, actually, because we know that h is getting smaller and smaller and smaller, they're getting closer to whatever that value was at x itself. So each of these is actually converging to f of x. I mean, you can see in the picture m of h is already equal to f of x, but that's only because we used an increasing function. Maybe m of h, right, started off much lower, right? Maybe you had some function that looked like this originally, in which case your m of h, your little m of h is going to occur down here, right? But as h gets smaller, all of a sudden this point's going to start moving over closer, and they're all going to converge to f of x. Okay, so we have this fraction, and it's bounded above and below by two functions which are converging to the same point, f of x. And we have a theorem for that. It's called the squeeze theorem. So by the squeeze theorem, right, which says whenever you have some function which is bounded above and below by two functions which are converging to the same value, then the function in the middle must also converge to that value. So this actually has to converge to f of x. So what did we get in the end? We took the derivative of this integral, we turned it into the definition of the derivative, and at the end of the day, we ended up with the original function f, which is what we said we're going to get. If we differentiate the integral, we get the function f. All right, so that's a proof of the first fundamental theorem of calculus. All right, so now we're going to try to prove the second fundamental theorem of calculus. So the first thing we want to note is we have an extra hypothesis going into the second fundamental theorem, which is now we're assuming that the derivative of the original function f is also continuous. And the reason we want to assume this is so that we can use the first fundamental theorem of calculus not on f, but on f prime. So if we integrate f prime and then differentiate, the first fundamental theorem of calculus tells us we get back to f prime, which tells us that the integral of f prime is an antiderivative of f prime, but so is f. So we have two different antiderivatives for f prime. One of them is f, and one of them is this accumulation function. Okay, that's pretty neat. But what do we know if you have two antiderivatives of the same function? They have to differ by a constant. And so what we'll show in the proof is that what is that constant? Well, it's going to be f of the initial point c that you're integrating over. Okay, so let's go down to it, and we'll give a proof now of the second fundamental theorem of calculus. All right, so f-talk 2. So we know, so by f-talk 1, right, by the first fundamental theorem of calculus, if I differentiate the integral from c to x of f prime dt, this is going to give me f prime back. Also, if I take the derivative of f, I also get f prime. So this tells me I have two antiderivatives for f prime. All right, but we know any two antiderivatives for f prime differ by a constant. Okay, so this tells us that if I integrate from c to x f prime dt, then this is going to equal the original function f plus some constant, right? And I can put the constant on either side. And I just want to know what that big constant c is. Okay, all right. So here's a little trick. I know this is supposed to be true for every x. I'm going to do it just for a particular x. What if I use little c? So x equals little c. Well, the reason I want to do that is because now, all right, of course, this is f of x, if you like. If I go to c, then I'm not accumulating anything, right? This is just going to be 0. On the other hand, this should be f of c, and then plus, well, big C. And so what does that tell me about my big C? That tells me that C is, well, just the negative of f of little c. Okay, so now we actually can rewrite this up above, right? So this line up above, we'll just rewrite it. So if I integrate from c to x, f prime dt, this will be f of x, okay, plus big C, but big C is negative f of little c, so minus f of c. And so there we go. That was actually what we were trying to prove. We knew that if we integrated f prime, we were going to get f back up to a constant, and that constant is precisely the negative of the value of f at this initial point. So that's actually how that initial point really matters, right? You may have thought when we did the first fundamental theorem of calculus that initial point doesn't really matter, and to some extent it doesn't. But for the second fundamental theorem of calculus, right, that's exactly the adjustment you have to make, right, to make everything work out precisely. Okay, very good. Well, that was our proof of the first and second fundamental theorem of calculus. I hope this is understandable. Please let me know if you have any questions.